Okay guys, recording number 2. So, we already tested on 5.1 and 5.2, and you are going to have a problem or two on this test from that section. So, the brunt of this test is going to be on solving equations, and so I'm going to cover those two sections last in the videos, alright? I'm going to focus more on the equation solving. Don't blow it off because it's a point or two. Watch all of them as they come out. Again, it's going to take a little while between me recording them and uploading them. So you have to bear with me a little bit on that. But you'll definitely have them all by Tuesday and in plenty of time to review for Thursday, in addition to the review in class. So we're going to start with basic trig equations from section 5.3. And what you want to look for in the basic equations are like terms that you can combine, either on one side or opposite sides of the equal sign, simple factoring, and or maybe you just have a few numbers like 2 sine x equals 3 or something, where you just need to isolate that little trig function very quickly and easily using a little bit of algebraic manipulation. So let's look at a problem here. I can already see I've got lighting issues here, so let's try doing this. I don't know if this is going to be any better for you guys. Hopefully it's not too bad. I see lines on my screen, so I don't know what that's from, but I apologize. No, that's worse. Let me just fix the exposure real quick. There we go. Okay, that helps. Alright, so we have this little equation. Sine of x plus root 2 equals negative sine of x. And I can see on both sides of the equation I have the same trig function, just opposite signs. So the idea is to get those things together. So I can do that by adding sine of x to both sides. When I add it to this side, I get a 0. And when I add it here, well, I get sine x plus sine x is 2 sine x, plus that root 2 equals 0. And now the idea is I always want to get this trig function isolated or by itself on one side of the equal sign. So to do that, you have to do your addition and subtraction first, then multiplication or division last. So I'm going to subtract root 2 from both sides, and then I'm going to divide both sides by 2. So I get the sine of x is equal to negative root 2 over 2. Now, what I know is, if I don't have my unit circle handy, and you won't during the test, then I know that the positive root 2 over 2 value for the sine in quadrant 1 is at pi over 4. So what that tells me is that even though this is negative, and I know that the sine is negative in quadrant 3 and quadrant 4, that I know that I'm going to have some kind of pi over 4 in quadrant 3 and quadrant 4. Well, to find the actual angle value in quadrant 3, I have to add this pi over 4. So I call this my reference angle because this helps me find where I'm supposed to be, or the angle I'm supposed to be. And I'm going to add it. If I want to go into quadrant 3, I have to add it to pi. So I have 4 pi plus pi is 5 pi over 4. And in quadrant 4, I'm just going to subtract that reference angle from 2 pi. So 8 pi minus pi gives me 7 pi over 4. So remember, an interval is not given here, so I'm going to say that x is equal to 5 pi over 4 plus 2n pi, and x is equal to 7 pi over 4 plus 2n pi. Those are just general solutions. I'm not restricted to an interval at all. Okay? I'm having coffee. So, here's another one. Okay. Again, it's very simple. There's not much I have to do, and in fact this one's easier than the one above it. So I have 2 cosine of x plus 1 equals to 0. So again, I just have to isolate this trig expression. So I'm going to subtract 1 from both sides, then I divide it by 2, and I know that the cosine of x is equal to negative 1/2, right? Well, I know cosine is negative in quadrant 2 and quadrant 3. And I know in quadrant 1 that the cosine equals 1/2 at pi over 3. So pi over 3 is my reference angle. So to get my quadrant 2 angle, I'm going to do pi minus pi over 3, which is 3 pi minus pi, or 2 pi over 3. And I'm going to add 2n pi to it because it's a general solution. And in quadrant 3, Well, to get into quadrant 3, I've got to add that reference angle to pi over, to pi. So we get 3 pi plus pi gives me 4 pi over 3. And then I'm going to tack on the 2n pi because it's a general solution. Okay, so this is like super simple, just a few steps. This one involved a little bit more because I had to collect like terms, okay? And sometimes you're just going to have to do that. And what these things do is they build up and up and up until they become more complex equations. Okay, another thing we can do with trig equations, when you have something squared, like this problem right here, the idea is we're going to isolate the trig function, we're going to get it by itself, and then we're going to take the square root of both sides. And I think pretty much everybody can do that without a problem. So again, to get it by itself, I've got to add 1 to both sides, divide by 4, and now I take this is by itself, so now I can take the square root of both sides. And when I do, 1's a perfect square and 4 is a perfect square. The square root of 4 is 2, so the radical can come off and I have plus or minus 1 over 2. So the cosine equals 1/2 at multiples of pi over 3. Well, in quadrant 1, that's pi over 3. In quadrant 2, it's 2 pi over 3. In quadrant 3, it's 4 pi over 3. And in quadrant 4, it's 5 pi over 3. So here's something that happens quite a bit. It's just an efficiency rule. But you need to know what's happening because, you know, if you're, for instance, taking a multiple choice exam, then what's going to happen is you're going to have to be able to recognize what's going on. So I printed out a copy of a unit circle and I filled in some things so I can show you as a reference. And I don't have my colored pens with me tonight because I left them at school, so tomorrow morning I'll go pick some up at Walmart so I can have some for the rest of the videos. But anyway, you know, I can write each one of these, right, as a general solution, pi over 3 plus 2n pi, 2 pi over 3 plus 2n pi, blah, 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 right? Or, what I know is from my unit circle, so here's the unit circle, and let me just move this up so we can get almost all of it in there. Focus. Woo. There we go. So I just printed this out, and what I did was I put some tangents in there to remind you for some other examples that we're going to talk about. But what I want you to see is this. The solutions here were many, right? There were 4 solutions. Well, I want you to look at where pi over 3 and 2 pi over 3 are in the unit circle. Here's pi over 3 right here. Well, here, I've got a yellow marker, but I don't know if it's going to show up well. So here's pi over 3, and 2 pi over 3 is here. Now, this is the y-axis. So these points are symmetric about the y-axis. They're the same distance apart, right? So the other thing I want to show you is from here to here, okay? From here to here is how many degrees? I have to go a half circle, right? So it's 180 or pi. So rather than doing, you know, pi over 3 plus, oh, and one more thing. For 2 pi over 3, right? If I take 2 pi over 3 and I just kind of follow the line, it's 180 degrees from 5 pi over 3, right? So what I want you to think of is this, that you can write all of these solutions here if you want to, or sometimes you might see it like this, pi over 3 plus n pi. Why? Because if I have pi over 3 here and I add 1 pi to it, I end up at 4 pi over 3. So it's covering this, pi over 3 plus n pi is covering this angle and this angle every time I go around, okay? If I add 1 pi, I end up here. If I add 2 pi, I end up here. If I add 3 pi, I end up back here, 4 pi, and so forth. You see that? Likewise, instead of me doing, you know, this one, that one, well, over here, 2 pi over 3 and 5 pi over 3 are pi away from each other. So I go around a half circle to get here. So I can just say 2 pi over 3 plus n pi, 1 pi, 2 pi, 3 pi, 4 pi, and I'll keep ending up in both of those spots. So by condensing all of these long, you know, solutions here into 2, because they're 180 degrees away from each other or opposite on the unit circle. We can condense it down into just these two solutions, which covers all of those. I hope that made sense. If not, let me know. Okay, here's another one here with remove. Oh, I almost forgot. So I wrote down an alternative method here. So you see this 4 cosine squared x minus 1 equals to 0. If that bothers you, if you feel really, I don't know, strange about the trig functions or whatever, you could always let u equal to whatever the trig function is. So in this case it's cosine of x, right? Don't worry about the square. Just let it be the cosine of x. Because what you're going to do is you're going to replace the cosine in here with a u. So what you end up with is 4u squared equals to 1. This may be easier for you to solve. We divide both sides by 4, we take the square root of both sides, and we get this. And at this point here, you can back substitute your u, cosine x is equal to 1/2, and what you end up with is the same thing, right? So here, here, I'm ending up at the same spot. So instead of doing the cosine, the tangent, the sine, whatever the trig function is, just let u equal to it and replace it with the u until all the mathematics is done. And then at the very end, substitute it back in. That way you can determine, which angles go with the value that you're given. And then you're going to continue on the same way. So here I need to find the rest of the angles at this point. So that might be a little bit easier for you. Here's another one. 3 cotangent squared x minus 1 equals to 0. So again, this is a very simple equation. I have to do a few steps, right, and take a square root. So I'm going to add 1 to both sides, divide by 3. Now I have my trig function isolated, so I can take the square root of both sides, and what I get is the cotangent is equal to plus or minus root 3 over 3. Now on this unit circle here, because I know that some of you have to keep referring back to it, and guess what? That's okay. Keep referring back to it, because the more you refer back to the circle, the better you're going to understand. So anyway, I want to look around my unit circle and say, where is the tangent equal to, the cotangent equal to root 3 over 3? Well, in quadrant 1, that's at 60 degrees, or pi over 3. It's equal to root 3 over 3. Now, according to what I have here, it's plus or minus root 3 over 3, right? So again, guess what? I'm going to end up with the same angles as the last one. I've got pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3, right? The same angles. And so, again, I can write them all out, plus 2n pi if I want to, or I can remember that pi over 3 and 5 pi over 3 are 180 degrees away from each other. So I can just say pi over 3 plus n pi, and I can also remember that 2 pi over 3 and 5 pi over 3 are 180 degrees away from each other. So I can write it as, this one, 2 pi over 3 plus n pi. Okay, again, the alternative to this, I'm going to let u equal to the cotangent of x. So you see what I'm doing? I'm replacing, instead of putting cotangent squared x, it's 3u squared. Okay, add 1, divide by 3, take the square root of both sides, and at this point here I back substitute what I let u equal to, and now I can go from here and say, okay, look on my unit circle and see where is the cotangent equal to plus or minus root 3 over 3 and get the angles. So again, this may be an easier method for you, and if it is, use it. Just don't forget to back substitute and find your angles. Okay, now we're going to go to true factoring. And there's simple factoring, and then there's quadratic type of factoring, and then there's trig functions where you have different trig functions in the equation, and you've got to use an identity to replace one of them to make them all the same, and then maybe you have to factor using a more sophisticated method, or maybe you could just factor very easily. So again, they can become more complex depending on what's given to you. This one's a very easy one. Now, I made sure to find a problem that had 2 different types of trig functions in there, so it's not too bad. And the nice thing about this one is I see on the left and the right, I have the same trig function, so I want to get those together to see what happens. So I started off by subtracting 2 cotangent x from both sides. And what I notice is I've got this minus this. This is a product, right? These are multiplied together. I can't add or subtract out of there. But what I can do is I notice that I've got 2 terms. I've got this term here and I've got this term here, and each one of these terms contains a cotangent. So that means that I can factor out a cotangent and rewrite what's left in parentheses. If I divide this piece by cotangent of x, the cotangents cancel and I'm left with cosine squared of x. Bring down the minus, and over here on this one, when I divide this by the cotangent, these cancel completely and I'm left with a 2. So now I have the product of 2 factors. I have cotangent of x times this thing equals 0. And whenever I have 2 factors, all I have to do is set each factor equal to 0 and solve. I don't have to factor anymore. I don't have to, even though this is squared, I don't have to, try and do anything weird with it. Just set them equal to 0 and solve. Okay? So when I set the cotangent equal to 0, I need to remember, when is the cotangent equal to 0? Well, if the tangent, so remember, those are those quadrantal angles, right, that I can never pronounce. But remember, this is the cosine and this is the sine, and the tangent is always the sine over the cosine, so I have it here, right? Well, if the tangent is 0 over 1, I know that the cotangent is going to be 1 over 0, and that's undefined. Oops, undefined, right? So that's not going to work for this particular problem because I want to know, when is this thing equal to 0? Well, if I look up here at the next quadrantal angle, which is at pi over 2, I see that I have the sine over the cosine, which is 1 over 0, undefined, but the cotangent is the cosine over the sine, so 0 over 1 is 0. So I know my cotangent is 0 at pi over 2. Alright, so I just say x is equal to pi over 2. Now, look, I put pi over 2 plus n pi because it's also going to be 0 down here at 3 pi over 2, 180 degrees away, right? So I'm done with that one. Over here, for this factor, when I set it equal to 0, I'm going to add 2 to both sides, and right away, I have a problem. Even if I take the square root of both sides of this thing, I'm going to have the cosine of x is equal to plus or minus the square root of 2. And the square root of 2 is bigger than 1, and so there's no solution for that. So the only solution for this particular problem is pi over 2 plus n pi. So again, I had 2 different trig functions. I had to collect like terms, so this was kind of a multi-step problem. I collected the cotangents over to one side, I factored a cotangent out, and then at that point I could set each one equal to 0 and solve for x. Here's another one. Now this one has an interval stated. And this is a cubic now. And that doesn't mean it's going to be harder. In fact, this is actually pretty easy. How do I know? Because first of all, I've got a cosine here and a cosine there, so that means I'm going to get like terms together and see if I can factor out something and make it a lot simpler. So I'm going to start by moving this cosine over by subtracting it from both sides. And then I notice this term and this term each have a cosine, so I factor out a cosine. And I rewrite what's left in parentheses. And now I have the product of 2 factors, and so I can set each one of those factors equal to 0. The cosine is equal to 0 at pi over 2 and 3 pi over 2. And again, I'm going to remind you with this circle that the x-coordinate is always the cosine. So whenever you see 0, comma something, your cosine is 0. So I know at pi over 2 and then 180 degrees away at 3 pi over 2, it's going to equal 0. So this one's done. Over here, I've got to add 1 to both sides. I've got to take the square root of both sides. Still not too bad, right? And now, I got to think, when is the cosine equal to plus and minus 1? Well, it equals positive 1 when x is 0, and it equals negative 1 when x is pi. So remember, we don't go back to 2 pi because this isn't included, and that's indicated by the parenthesis here. So I'm starting at 0 and including 0, but I'm not including 2 pi. So the possible solutions in this interval from 0 to 2 pi would be these 4 right here. And generally you'll see them written in ascending order. 0, 90 degrees, 180 degrees, 270 degrees, and so forth. Here's another one. We have 3 tangent cubed x is equal to tangent x. Red flag, same trig function. Opposite sides of the equal sign, so I'm going to subtract this one over and try to get them together, right? And when I do, I see that I've got common factor of the tangent, so I factored it out and rewrote what's left. And now I have the product of 2 factors, so I can set each one of those equal to 0 and solve. Well, we already know from the previous example that the tangent is equal to 0 at x equals to 0 and pi, right? Again, the tangent is the sine over the cosine. So this is the sine, this is the cosine, 0 over 1 is 0, okay? And the same thing's going to happen here. 0 over negative 1 is 0. So the tangent is going to be 0 at those 2 places. And so I have those 2 values. Over here, again, I got to do a little bit more work. I have to add 1 to both sides, divide by 3, take the square root of both sides, and if I clean this up by rationalizing the denominator, I get root 3 over 3. So, again, I need to refer maybe back to my unit circle, because pi over 6 and pi over 3 are the 2 that students get confused with the most, right? We've got a tangent of root 3 here, and the cotangent's root 3 over 3, and over here the tangent's root 3 over 3, and the cotangent's root 3, so they get confusing. And again, how I found those is just the sine divided by the cosine, all right, or the cosine divided by the sine if it's a cotangent. So, anyway, I want root 3 over 3, so I can see, right, from my unit circle that that happens at pi over 6. So, if it's plus or minus, there's no interval given. I'm going all the way around the circle, right? So pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And if I combine these with those are the potential solutions. And in fact, they're all the solutions because they all work. Okay, so if I were to plug these in, they would work. And a simple example, just so you know, because again, we haven't done too much work with this, and I'm not gonna hold you to this for this test anyway, to actually find the solutions, but in order for these things to actually be a solution, right, any of these answer choices we come up with, it can only be a solution if when we plug it in, then the left side equals to the right side. So when x is 0, for instance, if you always start with the original, if x is 0, you have 3 times tangent cubed, of 0 is equal to tangent of 0. The question is that true? Well, the tangent of 0 is 0, right? The tangent of 0 is 0, and 0 times 3 is 0. And on the right, the tangent of 0 is 0, so the left side equals the right side, so 0 is a solution. I might want to try pi. 3 times the tangent squared of pi, does that equal the tangent of pi? Well, when I think of a function squared, a trig function squared, I have to think of it as tangent of pi quantity squared. Is that equal to the tangent of pi? Well, what is the tangent of pi? The tangent of pi is 0. So in this case here, I don't even have to rewrite it to think about it. But I got 3 times 0 on the left, and 0 on the right, and 0 equals 0. So pi is a solution. And you just do that for every single one of these things. So that's where it can start to become a lot of work. And anyway, the ones that the left side equals the right side, those are your solutions. And the ones where you put them in and the left side does not equal the right side, then of course you would discard those. They would not be part of the solution set. Okay, next set, quadratic types. So these are of the form ax squared plus bx plus c, right? We write our x's starting with the highest power first and then in descending order, meaning we drop a power and then we have no x. Well, if you look at this problem here, even though I have sines and cosines in here, it still goes something squared plus something minus a constant, plus or minus a constant. So I do have this form here. And in this one, this is again a little bit complex. You can see all the work involved, but my trig functions are not the same. So the number one thing I have to try and do is try to make them the same. And I can do that by remembering my identities. And thankfully the Pythagorean identity for the sine squared is 1 minus the cosine squared. And I want to use that because I have a cosine here, right? So, it's hard for me to change this into a sine, but it's easier for me to change the sine into cosines. So I went ahead and I replaced sine squared of x with 1 minus cosine squared of x. Don't forget there's a 2 times that. And then you have to distribute this 2. So 2 times 1 is 2, 2 times negative cos squared x is negative 2 cos squared x. And then I just brought the rest of this stuff down. Now, I want to try and clean things up and collect like terms if I can. Well, these two are not like terms, but the numbers are. So positive 2 and a negative 3 give me a negative 1. So I end up with this right here. And the one thing we don't want is a negative hanging out here. So all you do is multiply every term by a negative 1, both sides. 0 times negative 1 is going to be 0. So on the right hand side it's not going to matter. And all that's going to do is just change the sign from negative to positive, positive to negative. So you can see the signs changing between those two lines there, right? Once I have this, now I can go ahead and factor. And, you know, I factor by, I don't even think there's a name for the method. We used to call it trial and error. But what we do is we take the factors of this leading coefficient here, so 2 and 1, so we don't write the 1 there, but 2 times 1, and we put an x here and an x here, or in this case a cosine x and a cosine x, and then we find the factors of 1 such that when combined with this coefficient 2, when we add or subtract we get a negative 3. Well, this is negative and this is positive, so I know both of these have to be negative in here. So if I put a negative 1 here, I get negative 2 cosine x minus cosine x is negative 3 cosine x. So bingo, I know that I factored it correctly. So now I've got the product of two binomials. I can set each one equal to 0 and solve. When I solve this one here, I add 1, divide by 2, and then I say, hey, I remember from my unit circle that the angles whose cosine is 1/2 are pi over 3 and 5 pi over 3. And over here I'm going to add 1 to both sides, and this is nice and simple because the cosine of x equals 1 only, at one place, and that's at x equals to 0. Now, there's no interval given, right? So all I'm going to do is add a 2n pi onto each one of these. So, at x is equal to 0, it's 0 plus 2n pi, so we just write it as 2n pi. If you want to write it or think of it this way until you get used to it, that's fine. These are the same. Oops, I'm sorry. These are the same, okay? And for the rest of them, pi over 3 plus 2n pi, 5 pi over 3 plus 2n pi. Capiche? And the last page for this section, there's another one. Now this kind of looks quadratic-y because I have something squared, and in fact, it is. Now by the way, these are squares, don't confuse them with the double angle. I haven't gotten there yet, so these are squares. And again, my trig functions are different, so the very first thing I want to try and do is make them the same by using an identity. So, you could have used the identity for the tangent, you could have replaced this, right? I decided to place the secant just because I prefer to work in tangents and not secants, but you could do whatever you want. Anyway, I know that secant squared of x is 1 plus the tangent, and I forgot my 2 here. Alright, so this is 2 times 1 plus the tangent squared, and then I brought everything else down. And so if I distribute, this is 2 plus 2 tangent squared of x. I gotta be careful here, so hang on. Let's move over to this side, okay? So I don't make, because I made a mistake, I forgot the 2. So when I distribute, I get 2 plus 2 tangent squared of x. And bringing the rest down, I get this, right? And I can see that the 2 and the negative 3 can go together, so I'm going to write this as 2 tangent squared of x plus tangent squared of x minus 1 equals to 0. And then I see that these two are like terms, so I can add their coefficients and write that as 3 tangent squared of x minus 1 equals to 0. And then all this becomes at this point now is something where I'm going to have to, add, divide, and then take the square root. So I'm going to add 1 to both sides, divide by 3, and take the square root of both sides. So I'm going to rationalize, right, this is the square root of 1 over 3, which is root 3 over 3. Okay, now you notice when I made the mistake over here, I've got pi's over 4, right? Because the tangent's not 1 anymore. So missing out on that 3 when I divided, I ended up with a 1. So scratch that. For this particular problem, this is correct. And, when does the tangent equal to root 3 over 3 again? Well, if I need to, I can take out my unit circle and remind myself that the tangent is equal to root 3 over 3 at pi over 6. So what I know is that I'm going to have x equals to pi over 6 in quadrant 1. In quadrant 2, that's going to be 5 pi over 6. In quadrant 3, right, we're going to have 7 pi over 6. And in quadrant 4, we're going to have 11 pi over 6. So we're going to have these 4 answers. An interval was not given, so technically I would put plus 2n pi, but I'm just going to be a little bit lazy. Don't you be lazy on your test, but I'm trying to save time because the longer I make the video, the longer it takes to upload it. So just for a time saver, I'm not going to go ahead and write those out. Okay. Again, the other thing with this is, when you get to this point here, again, if you want to use that u substitution, you can say, 3u squared minus 1 equals 0. 3u squared equals 1. U squared is 1/3. U is plus or minus root 3 over 2. And at this point here, I would back substitute what I let u equal. Well, I always let u equal the trig function, and so in this case it's the tangent of x. So I'd say tangent of x is plus or minus root 3 over 3. That's a 3. And then at that point there, I would start finding my angles on the unit circle. Okay. Finally, a couple more examples on these multiple angles. So we're not using a double angle formula to expand anything. We're trying to solve these trig equations. So I have 2 cosine. So this isn't cosine cubed, it's not cosine squared of x. Now I have something times x in here. So that's how I know I have a multiple angle. It could be a 2x, a 5x, a 10x. It could be x over 4, x over 2, whatever. All right? It's a multiple angle. So again, I'm going to proceed just like there was an x there. I'm going to add 1 to both sides, divide by 2. All right? The only thing I have to be careful of is, I think, when is the cosine of x? So I pretend like there's an x there. When is it equal to 1/2? Well, I know in quadrant 1, the cosine's positive, and that's at pi over 3. And I know it's positive in quadrant 4, so if I do 2 pi minus pi over 3, I get 5 pi over 3. So these are the 2 places in the unit circle where my cosine is going to yield a positive 1/2. The only thing is I can't say x equals pi over 3 and x equals 5 pi over 3, because there's a 3 here. So I have to show 3x equals pi over 3 plus 2n pi, and 3x equals 5 pi over 3 plus 2n pi. And then I divide each one of these little pieces in each equation. So let me just, I forgot to add my 2n pi in there earlier because I was trying to get this done fast. So these are 2 separate equations, right? There's 2 possible angles for which the cosine is 1/2, so I'm going to end up with 2 equations. And now I'm going to divide by 3 both sides, each piece. When I divide this by 3, I end up with an x. And again, you can think of this as multiplying each one by the reciprocal of 3, which would be 1/3. So if I multiply this by 1/3, I get pi over 9. And if I divide this by 3, I get 2 pi over 3. So I get pi over 9 plus 2 pi over 3. And on this one here, if I divide by 3, I get 5 pi over 9 plus 2 pi over 3. The final multiple angle one, I thought I'd put a fraction in there for you, because you never know what's going to be on the test, right? Anyway, Again, this really isn't a difficult problem. I have to subtract 3 from both sides, divide by 3, and I get the tangent of x over 2 is equal to negative 1. So again, I want to know, when is the tangent equal to negative 1? Well, I know that it's going to be at some multiple of pi over 4, right? The tangent in quadrant 1 of pi over 4 is 1. So I have to think of the quadrants, where is the tangent negative? Well, the tangent's going to be negative in the quadrants where the sine and the cosine have different signs, S-I-G-N-S. So quadrant 2 and quadrant 4 is where the tangent is going to be negative. So I have to say, in quadrant 2, if this is a multiple of pi over 4, well, if I subtract that from pi to get my quadrant 2 angle, it's 4 pi minus pi, or 3 pi over 4. And in quadrant 4, 2 pi minus pi over 4 is going to give me 6 pi over 4. I'm sorry. Oh, yeah, sorry. This is tangent. I forgot. Sorry, my bad. So remember, the interval for tangent is from 0 to pi. So technically speaking, there's one solution from 0 to pi. So here's 0, here's pi. And the tangent, here's 0, here's pi. And the tangent solutions are in that interval. So anyway, there's one solution. The tangent is going to be negative 1 in quadrant 2 then. So it's going to be 3 pi over 4 plus n pi. We know it's also negative in quadrant 3. So if I add, if this is 3 pi over 4 here and I add 180 degrees or 1 pi to it, I'm going to end up with my quadrant 3 angle. So anyway, at this point now I'm going to multiply every piece, both sides, by a 2. So I'm going to have 6 pi over 4 plus 2n pi. And then I can reduce this little fraction down to 3 pi over 2 plus 2n pi, and I'm done. Alright, so I hope that helps. Again, this is section 5.3. Sections 5.4, 5.5, 5.1, and 5.2 will be forthcoming. See you later.